So I've got the first presentation that runs up to 9:30, and it's really just trying to be an overview of the complex ore bodies program to date. And it borrows a little bit from a presentation I gave a few months ago, which I've tried to update. There are a couple of bits that haven't been completely updated, but hopefully no one will mind that. So we'll get going. Oops. So what's already been mentioned is that we called it the Complex Ore Bodies Program, but really you could also call it the Future Mineral Supply Program, because the reason that we're trying to understand complexity in the development of mining projects is because of the fact that there are a whole lot of important reasons relating to the future of the world that require future mineral supply. And I'm not going to go through all these, but when you look at the Sustainable Development Goals, there's a whole series of pieces around mining, poverty eradication, decent work, infrastructure, reduced inequality, the fact that we, the lucky 1 billion people, can't sit here and enjoy what we enjoy and deprive the other 6 billion of people on the planet from something approaching the same sort of thing, or even when we consider the requirements of the coming energy transition in terms of future metals, future mineral supply is going to be absolutely essential. And that future supply is going to have to come from known ore bodies. When you look at the future demand, and again, this is from quite a seminal paper, Elshkaki et al., just looking at a whole range of different commodities, and that gray bar essentially shows where those commodities start to, the band over which the projected shortfall of those commodities starts to intersect with demand. And you can dispute about whether, how believable that is. And there are various different viewpoints about it, but there's no doubt that future demand is going to continue to grow, and there's going to be a requirement for future supply. When you look at a lot of commodities, and we're looking at copper here, there is a strong and growing portfolio of copper, of lithium, of a whole range of different things that we know about. But the problem with a lot of it is that if we continue on our trajectory, and I'm going to touch on this a little bit this afternoon, if we continue on the trajectory that we're following to produce it, we're going to create exponentially larger problems around disposal of waste, tailings, disruption of communities and environments, biodiversity, and so on. And of course, what's also operating at the same time with this is that there's a general trend, because the Earth is finite, that new discoveries are decreasing. And this is just a graph from Minex Consulting, Richard Shoddy, showing that the rate of discoveries and mineral expenditure and discovery expenditures, and there are disputes one could go into about the time lag of expenditure and discovery and that sort of thing, but the reality is that in the recent times a lot of exploration work has actually been value destructive. And then the other argument, and I know that most of you are probably aware of this, and this is again from that same Elshkaki et al. Paper looking at different global future scenarios, this time for zinc, but the same thing applies for copper. For the medium term, at least for the next few decades, recycling can't meet our future demands, the future demands that we need to meet the Sustainable Development Goals, to complete the clean energy transition, to do all the various different things that we need to do in order to I guess achieve the important environmental goals and social goals, whilst I guess meeting an increasing world population. And So one of the things that we've been spending a lot of time doing, and we'll talk, there'll be a few talks talking about this, and one of the central ideas of complex ore bodies was that when we're talking about complexity, we're talking about all the complexities that face mineral development, not just low grades. In fact, what I'll argue, probably not so much in this talk, but this afternoon, is that low grade is probably the least of our problems. Other technical challenges, but political unrest, social outrage, environmental barriers, regulatory barriers are probably more of a challenge than those other factors. So this is a really fast overview of the research that we've been doing to try to address some of those challenges. And I'm just going to go through these one by one, and I'm really going to not spend too much time on any of them, because there are going to be, and I might mention some of the talks, better get the schedule here to make sure I don't leave anyone out, mention some of the talks that are actually happening today that will be addressing some of these, that will be, I guess, presenting some of the work that we're carrying out relating to some of these challenges. So one of the first things that we started doing was trying to develop an understanding of what the actual challenges were to future mineral supply. Because when we actually worked out that this program was kicking off, I started a process of just going out and finding all the different future mineral research roadmaps, and there's a lot of them. There really are a lot of them. And what I found was that a lot of them were guided by the particular specialty focus of the group that was considering those roadmaps. And a lot of them weren't really based on any sort of a database of what the actual challenges were. So we've actually devoted a lot of effort and a lot of smart people, transdisciplinary people's time trying to understand this problem. And we're going to hear a couple of talks in that area today from Eleanor Leb, Kamila Svobodova, and Laura Saunter on aspects that relate to that. And we would have heard from Shabir Ahmad as well, but unfortunately he's had a tragedy in the family and won't be able to come today. And all of that work has gone into trying to understand not just I guess the magnitude of the different and relative importance of the different technical challenges, but also the more granular detail of what those challenges are, with the aim of guiding the solutions that we seek across those different areas. And having identified those problems, now how can we come up with research that will address some of those challenges? Now, the next and vitally important piece, and one of the most industry supported areas of our research program, is in the area of community and social performance. And that's an incomplete list of pictures across the bottom. We're going to be hearing from Nick Bainton and Anthony Kung today, talking about various different aspects of this. And these slides are actually from previous presentations done by the Center for Social Responsibility in Mining on various different aspects of this problem. As we've done more work, what we've realized increasingly is that this is probably, if you were going to narrow the challenges down to one, this would be the one you would probably land on. I think that CSRM has made it abundantly and convincingly clear that this isn't a program about convincing communities that we should allow them to develop their mines. It's a program about understanding the complex, the incredibly complex mix and interplay of challenges that lead to impediments to mining, in order to guide, I guess, the mining industry towards solutions that will lead to greater acceptance of their efforts to improve mineral supply. We're also we've had various iterations of trying to quantify some of the, I guess, some of the rarely quantified aspects of mining projects in terms of their, in terms of how we place value on them and how we assess costs and risks associated with different aspects of mining. So we earlier on, and I haven't shown that here, but we had Malcolm Powell and Junyu Wang and Grant Ballantyne worked on some modeling related to incorporating social innovation into formulation of mining projects. And then Brunhilde Verrier did some very interesting work working with Carl Smith from the business school and Mosen and Gordon and Marson on an attempt to quantify some of the effects of cyanide as they in terms of the interface between a mining project and the community and the environment. And what we're currently doing now is taking Mehdi Azadi and company's paper, and I could probably put a number of other people on here like Mansour and Salim Ali and so on, relating to greenhouse gas accounting around mining projects and the mining value chain, and to place it into that same sort of system dynamics framework. And Mehdi's going to tell us something about that today. Of course, one of the other things that is a very important thing to study is to say, well, there are some areas where maybe any sort of a mine, whether it's underground or open pit, is not going to be suitable. It just can't be done. And so recovering metals without mining at all and producing an absolutely minimal effect on the environment is a very important area. It's probably, you know, projects like that do exist, but not for a lot of the metals that we need to supply some of the future generations. So we've gone through a process of identifying a lot of the university's skills, what we could bring to the table in this area. But I guess what I would have to say is that up to now, we haven't focused on all of that area. What we have focused on is one of the key ones, which is if we're going to start pumping fluids down into the earth and trying to recover metals with them, we better make sure that those fluids are efficient and benign. And one of the main projects that we've been working on, and Professor Gary Schenk is going to be talking about that later today, is on development of novel lixiviants using enzymes to carry that out. So that's an area that we've been focusing on as a component of that broader ambition to advance knowledge about in situ recovery. How am I doing for time? Not too badly. Of course, the other thing, and I'm going to be talking about this afternoon, and this is a very busy slide. It's got lots and lots of people on it, but the summary point about this area, understanding variability and flexibility, and I'll develop this argument a little bit this afternoon, is that when you look at most commodities, I'm sure a lot of you are tired of hearing that demand is going up, grades going down, so waste is going exponential. Demand's up, grades down, waste's exponential. Tailings are exponential. And at some point, we're going to reach the limit of that equation. And the potential solution to that is to develop means to understand variability in ore deposits better, and to mine and process those ore deposits using that understanding of variability in a more flexible way. So we've been devoting a lot of effort to understanding variability, trying to develop more flexible processing, and trying to develop the tools that would allow us to understand and propagate that understanding of variability into mining and processing. We've also, there's been quite a lot of effort and a very large number of publications relating to aspects of and Camilla has been one of the big drivers behind this, looking at aspects of mine closure using the mine database that we've been working on, the mine understanding that we've been working on. And some of this slide, as you can see, actually predated the formation of CRC time. We now have CRC time, and this program is really interfacing, I think, quite well with CRC time to continue this work. Another critical, another very important aspect of the, I guess, the energy transition that we need to go through in the future is to understand how to extract, to develop a better understanding about how to extract some of the metals that we're going to need, like the selected rare earth elements that are absolutely essential for magnets and batteries sustainably. And so we have a very multidisciplinary project going on in that area. In fact, a lot of the people involved in it just arrived back from Mount Isa, looking at conventional hydrometallurgical or unconventional hydrometallurgical approaches, biogeochemical approaches, and phytomining approaches to, and hybrid flow sheets for sustainable treatment of rare earth elements. I guess a lot of you would be aware that some of the rare earth elements that we're recovering now are not being done in the most, not being recovered in the most sustainable way.
I uploaded, I tried converting video and I uploaded it to your file or your drive.
Yeah. Could you just, whoever's talking, could you, it says talking Rick Valenta, but I don't think I am talking, but anyway. Well, I am talking, but somebody else is too. The other vitally important area for all of this is, for so many things, and we've really only scratched the surface in this area, is water. And we'll come back to this when we look at processing as well. So water, competition for water is going to continue to increase. Sensitivity to contamination of water supplies is going to continue to increase. And novel ways of making water available for mining projects without competing is going to continue to increase. And Liliana is going to talk about some of the work that's going on in that area. Within between, I guess, between SWMI and also SMI's Chile. We have a couple of projects, one of which is less active right now, the other of which is our biggest project in terms of external industry funding. In removal of contaminants from the mining value chain. So when on the left-hand side here, we've got diagrams that describe, at the top there, it's really just looking at arsenic levels in concentrates and showing that they've increased over time. And we have a program that we're continuing to try to push forward on novel ways to remove arsenic from the mining value chain in a more innovative way. So that's one side of this work. The other side is a whole range of projects supported by a number of different groups, looking at understanding mine waste, using geometallurgical techniques to predict mine waste challenges, and also to consider to I guess characterize and understand the means to remove or to realize value from mine waste. And we only have one talk on this today. We could probably have a whole day on this because there's a large number of projects operating in this area. But Mansour Adraki is going to be presenting a very interesting, I guess, summary of the work that predominantly his group, but collaboratively with the BRC, are doing on the Wolfram Camp deposit in North Queensland. And then this one, I guess producing metals using less energy and leaving safer tailings. It's probably a good point for me to say that there is a very important role for mineral processing in this area. What we've focused on in this project is the areas that of innovation that have the greatest potential to reduce mining footprints. So in other words, we haven't had a lot of interest in getting another 10% improvement in a SAG mill, or because I think that work is quite well addressed here and elsewhere, and it's not going to transform. Anyway, I don't want to bag that work anymore. It's very important. But the work that we're focused on is mineral processing that can use less water, that can result in tailings that can be dry stacked rather than have to go in a wet tailings dam, and that can result in savings in energy. Therefore, producing a project that has less of a footprint and less problem with the the non-technical challenges that are proving to be so important in this area. So Frank Shee is going to talk about some of our high voltage pulse research, which has great potential in that area to eliminate material that should never make it into the plant. And Lisa is going to be talking about our coarse particle flotation research that is now supported by a large consortium of companies. See what I mean, Neville? I didn't have any trouble using up the time. Oops. What's been the impact so far? And basically we started in 2018 and we had $5 million strategic funding from the university and an undertaking in our proposal to match that with $7.5 million external funding. Another very important aspect to us was to only focus on projects that were collaborative. So in other words, they weren't sort of silo projects, they were cross-disciplinary projects, and to focus on projects that involved groups outside the SMI. And so we've ended up with, actually it's more than 89, because as I was producing this presentation, I realized that I'd left some people off of the photo I'm going to show in a second. So it's probably more like 93, I think. Researchers from UQ participating and those from elsewhere as well. We've exceeded our funding target so far and are on track to well exceed our overall external funding target. So now that means we're focused on delivery and maximizing impact for the project. So we've got about 21 projects going on that, depending on how you count it, involve about 15 different UQ schools and centers. So it really is a cross-cutting program in that sense. A lot of collaboration, a lot of external funding partners. So again, you can count that slightly different ways, but that shows roughly the order. Again, the journal publications number is a little bit fluid because we've actually had 2 more accepted in the last couple of weeks. So, and we provided funding to a large number of HDR and postdoctoral students, not postdoctoral research fellows, not 100% funding in some cases, but funding to carry out important work. We've actually managed to seed fund a lot of interesting projects, many of which have gone on to prove concept and bring in external funding. We've had an international conference. This is a second presentation day and a couple of patent applications as well. So I think I'm fairly satisfied to date with our impact. Just a snapshot of some of the companies that have been involved. It's quite a large group, so again, I think that's across a large number of projects, and in terms of external universities, we have had quite a lot of collaboration with people outside UQ. And then what I want to end on is just to say, this is the list of, or the set of photos that I compiled of people who have been involved in some way over the last 2.5 years in the Complex Orebodies project. Like I say, there's about 3 or 4 people missing in that. If you don't find yourself there and think you should have been there, I'd love to find somebody else to blame, but I can't find anyone. So I guess it'd be me. And thanks very much. That's all I wanted to say.